Okay, in this project, we're going to talk about the angular momentum. And everything for here, I have to emphasize that it copyright from the Cengage Learning Center. The first one, the angular momentum L, is defined for a particle of mass moving with translational momentum vector p equal to m times velocity, where the L, the angular momentum L in here, is the vector quantity, and which is shown in this equation, where the angular momentum L is proportional to the cross product of R, the vector, cross product by the P, which is defined by the mass times the velocity, where R is the position vector of the particle pointing from the origin of the coordinate system to particle, which show here this picture shows the exactly what here the definition over here. The cross product is over here from the origin. The R over here is the blue segment vector, and from the Z to the particle, which is a vector. Because the angular momentum can be determined by using the vector cross product, its direction can be found by using the right-hand rule. The vector L must be perpendicular to the plane containing the vectors R and P. As with alien cross product, the magnitude of angular momentum may be found by R equal to A times B sine theta. Okay, A times B sine theta, which we have the angular momentum is equal to RP sine, this one could be equal to theta times its angle between R and P is equal to R perpendicular to P or R perpendicular to P, where this guy, the theta, is the angle between the vector R and P, the vector P, and R is the component of R that is perpendicular to P, and P is the component of P vector P that is perpendicular to R. The SI units of angular momentum are kilograms times meter square per second. Okay, next slide. And here we'll show an example. I will give you an example of how to define the direction of the angular momentum. The example, the figure below over here shows a particle with momentum p using the coordinate system shown. Determine the direction of the angular momentum of the particle around the origin in each case, and write expression for L, which is the angular momentum, using symbols defined in the figure below. Okay, therefore the first case will be the L, the angular momentum is negative R times P, sine angle in k direction, because the angular momentum is into the page in the negative z direction. Next one, the R is parallel to P, there because the angular momentum is 0 because R is parallel to P. Then the last one will be in case 3, will be the angular momentum is out of the page in the position z direction. So we have the angular momentum is equal to R times P times sine theta times in k hat. So here will be some derivation of the angular momentum of a rotating ridge object, which here will be defined this formula, which will be the angular momentum equal to I times omega, which omega is a vector again. Therefore, the angular momentum of each particle is given by L, the angular momentum R cross P. So this is 1 and 2. For then, by the right-hand rule, both L1 and L2 point in the positive z direction. From the picture, R is perpendicular to P for each particle, so we can write like this: R times P. Therefore, the angular momentum L of the entire object is the sum of L1 plus L2. So we have this. We can derive the first formula L1 plus L2 because the L1 equal to this and L2 equal to this one. So we can write like this. From the P equal to m times V, which the previous formula, we can write the L in terms of the mass and velocity of each project. So given by this formula. And both particles have the same angular speed omega related to their translational speed by velocity equal to omega times r. So we think we have those formulas. Then after that, the angular momentum is equal to I times omega times in k hat. Then we have this formula.
Alright, so this is my part of the project of angular momentum, and I'll cover the conservation of angular momentum. As we learned in chapter 10, when no net force acts on a system, the system translational momentum is conserved, and this principle gave us a way to analyze complex issues such as decay of a nucleus. In this section, we learn one how to apply the principle of conservation of angular momentum. In this slide, we will explain how to express Newton's second law for a system. Another way we can express Newton's second law for a system is where the total external torque exerted is the system's total angular momentum. As we can see, the equation holds for a single particle, a collection of particles, or an object. Our derivation is made simple to consider a single particle moving along a straight path. A net force acts on the particle so that it speeds up along the path. We will show that for this particle in the next slide. As we can see from the picture, the particle moves in a straight line, and R moving in the right direction is its constant, and a net force acts on the moving particle. Because the particle speed increases, its transitional momentum also increases. The particle's path is also along the straight line shown, so R torque does not change, but because the transitional momentum P increases, the particle's angular momentum L around the z-axis also increases. In this slide, we will talk about formulas that we use for the angular momentum. As we can see, L equals R times P, and then we take the derivative of the formula, and then we use the chain rule to expand the right side, and then we cross multiply each term, and then rewinding the derivation of the first term. We rewrite the derivative in the second term using a general form of Newton's second law, and then as a result we get this formula: d over dt rp equals 0 torque total. And then finally, so a net torque on a particle changes its angular momentum, so the derivative is d over dt L torque total. In this slide, I'll provide an example by using Kepler's second law. According to Kepler's second law, a line joining a planet to the sun swept out equal areas in equal times. We'll use this principle of conservation of angular momentum to prove Kepler's second law. As you can see by the figure, we have dA1, dA2, and a Kepler's second law says dt1 equals dt2, then dA1 equals dA2, and so it can be written as dA over dt equals constant. To solve this mathematically, we use physical concepts and mathematics to prove it. Our results from the first figure shows the angular momentum of a comet Halley is nearly constant as it orbits the sun. It lets us see the if a particle such as a planet in orbit around the sun meets the condition for conserved angular momentum. We assume on other planets and objects in the solar system exert negligible force on the planet, and only the force acting on the planet is Fg due to the sun's gravity. And the formulas we use and the other formulas we use for this solve are r times I equals P equals RF times PF, which is we can say R initial times P initial equals R final times P final, or we can write it as I initial times IW equals I final times W final. In this figure, we can see the planet of a mass m and the sun, because the angle of between R and FG is 180 degrees at all times. There is no torque acting on the planet, and its angular momentum around the sun is conserved. And we can see the formula torque equals R times Fg. We can also be written as T equals R times Fg sine 180 degrees equals 0. Writing in the expression for the planet's constant angular momentum, it can be written as L constant equals R times M, or it can be written as M times R times V